Hi, I'd like to introduce the speaker. This is Dr. Joshua Cooper from the University of South Carolina. Just on a personal note, Josh managed to catch me before I had learned about proofs, and we've worked on projects since then and kept in touch, and he's been an important person in my mathematical life. And I'm glad he was able to come this week. Oh, and the title of the talk is some linear algebra, so pressing sequences and binary matrix algebra.
Thank you very much, and thank you for the invitation. So what I'm going to talk about today started out as work with, you may have met Jeffrey Davis at some point. He's at Emory at this point, and but now Hayes, my current PhD student, has kind of picked up the work and run with it, so that's largely what I'm going to talk about. All right, this actually comes from a strangely applied problem. Basically, in phylogenetics, one of the main problems is to reconstruct the evolutionary history of all organisms, right? There's a tree that we only see the leaves of, and you want to know everything that happened before. One way to do this, let's say you've got two genomes here, so here are two genomes, is to compare them and say, how far apart are they? But how do we measure how far apart they are? Well, there's certain kinds of transformations that occur over time. Now, you may have heard of SNPs, single nucleotide polymorphism. These are very small changes, right? These are single letter changes that occur. At the genome level, sort of macroscopic level, there's other changes that occur. And the most common, I'm told by my biology friends, is the subsequence reversal. So basically, during mitosis, the DNA gets copied, and then it breaks somewhere accidentally. Now, normally, this means that the cell that ends up being the descendant is not viable. But every once in a while, it, by chance, reattaches, and then it's okay. And then also, and of course, you get the same organism now. Also, every once in a while, by chance, it reattaches the other way around, because DNA points both ways. And so that's a subsequence reversal. Right, so the question is, and this is this very common transformation that can occur on genomes. And so the question is, how far are these two genes apart, species 1, species 2, in subsequence reversals? Because this is some measure of the distance to the most recent common ancestor of the two organisms. Right, that's the intuition. So in the original paper that posited this, it says something like, how to tell the difference between turnips and cabbages, or how far apart are turnips and cabbages. So turnips and cabbages, that's what these are. And so the question is, if you think of this first genome as 1, 2, 3, 4, 5, and I've color-coded them so you can see, how did that turn into 2, 1, 5, 3, 4? What's the most likely explanation? That is, what's the highest probability sequence of events that occurred that would have led the first one to turn into the second one? Now, to be sure, the first one didn't actually turn into the second one, right? Cabbages didn't evolve from turnips. But there was some organism that evolved into both, and so there's some sequence of transformations that'll get you from one to the other. And trying to minimize the length of that sequence gives you a reasonable approximation of the distance between the two genomes. So, well, like I said, some sequence of reversals of subsequences actually was the thing that got you from one of these genomes to the other. So just for example, if you took these first two genes, so that this is 5 genes in a row, right, along a chromosome. Take these first 2 genes, and you flip those 2, you get this, and then you flip these 3, you get that, and then you flip those 2, you get, this is one way to transform this sequence into this sequence, right? And it turns out that's the shortest sequence. It takes 3. You have to do all 3 of these flips. Or you can do it on other sets of 3 flips, but you need at least 3. Interestingly, in general, reconstructing the shortest, that is most evolutionarily likely sequence of swaps, is NP hard, which is really unfortunate because organisms in the real world tend to have lots and lots of genomes, and so you don't stand a chance of finding the minimum length sequence of swaps. However, something amazing about this, you wouldn't think it would help, but there's a little tiny bit of information we've thrown away in this picture, which is the direction of the genes, right? So the idea is during transcription and translation, there's a reading along the strand that heads in one direction or the other. And actually, information can be coded on either side of the strand. And so these genes have a direction that they're supposed to be read in when turning it ultimately into a protein. So what if you keep track of the direction? So if you use that same sequence of flips, then, okay, now there's 1 bit per gene here that we're keeping track of, right? So we'll say it's 0 if it didn't get flipped, and 1 if it did. So the green, for example, did get flipped, it gets a 1. This addition just 1 bit. You think n factorial is a lot bigger than 2 to the n, but still, this is some additional information, and really what this has done is it's turned the problem of sorting permutations by subsequence reversal into sorting signed permutations by subsequence reversal. The idea is a signed permutation is a permutation where you put plus or minus with each of the elements, and then the subsequence reversals are going to switch the signs too. Right? So the question is, how did 1, 2, 3, 4, 5 change into -2, -1, -5, 3, 4, which is this bottom permutation, because those are pointing backwards. And a really striking theorem of Hannenhalli and Pevzner from the late 90s, although they more or less anticipated in the mid-90s, it turns out this makes it polynomial time. There is a polynomial time algorithm for finding the shortest sequence of subsequence reversals if you've got this little bit of additional information that is the direction of the genes in the 2 genomes. So subsequence or signed permutation sorting by subsequence reversal is actually p time, whereas as far as we know, the subsequence sorting by subsequence reversal of unsigned permutations is currently not. And now at the core of the proof, if you look at this proof, it's like buried in biology. But if you dig out the core of the proof and see what's going on, you'll find that what really matters to it is the existence of what I'll call a successful pressing sequence. In fact, we want the shortest successful pressing sequence. That essentially corresponds to the sequence of transformations, these subsequence reversals that are occurring. And they're occurring, a subsequence, I'll tell you exactly what it is in a minute. It's something that occurs on a bicolored graph. So that's a bicolored graph. Bicolored graph is just a graph where you've assigned 1 of 2 colors to each of the vertices. It's not a proper coloring or anything. There's no restrictions. I've just colored the vertices black or white. Okay? So I got to tell you what pressing is. And just a note, I put a little star, little asterisk. I'm going to say something about the existence of this shortest pressing sequence in a moment. It doesn't always exist, but essentially it does. So here's the idea. When you press a vertex in a bicolored graph, you have to press a black vertex. You cannot press white vertices. And when you press a black vertex, what it does is complements its neighborhood. And by that I mean it flips all the colors of that vertex and its neighbors, and also flips the edges to non-edges and non-edges to edges in its entire neighborhood, okay? So, for example, if you go to press that vertex, this is why I'm using PowerPoint, so you can see these colorful animations. So you press that vertex, right? It should turn that vertex white, black, black, get rid of that edge, get rid of that edge, get rid of that edge, rid of that edge, but put that edge in. And, oh, and I guess there's another edge right there that got put in. So that's what you get after pressing. Now notice, after you've pressed, you're done, you can never touch that vertex again, because it's just been turned into an isolated white vertex. So vertices that are pressed are essentially thrown into the dustbin and can never be used again for pressing. So let's say you go to press that vertex next. Okay, so it does that, press that one, press that one, press that one. That's what we'll call success. That is, you empty out the graph, you get rid of all the edges, and all the vertices end up white. Right? That's a successfully pressed graph, or a successful pressing sequence. And then the little asterisk that I mentioned earlier, this always exists if the graph has a black vertex in each component. That's, surprisingly, it's not trivial. It's not hard to prove that, but it's not trivial. You might have thought as I was doing this that you could just greedily press black vertices. But that's actually not the case. If you look, when we're at this stage, if you tried to press that vertex, you get stuck. This happens. There's nothing you can press, and you haven't gotten rid of the edges. So actually, you can't greedily press. Essentially, if you could just maintain there being a black vertex in each component, then you're fine, if you believe the previous statement. And so if you just look ahead for each, but the existence of a vertex that preserves that property is not immediately obvious. All right, so the pressing sequence for this graph that I just showed you is, I'm just going to order the vertices by when we pressed it. So that was the first press, that was the second press, third press, etc. And what I'm going to do is, given a labeled bicolored graph, G on n vertices, we define this augmented adjacency matrix. It's really, it lives over F2. So we're going to put a 1, it's just like an ordinary adjacency matrix. You put a 1 there if the column and vertex numbers correspond to vertices that have an edge between them. And, but we'll also put a 1 on the diagonal if the vertex is black. Okay, so that's where the augmenting is happening. So for example, this graph has that as its augmented adjacency matrix. That's G. You might notice that there's another graph that this really is the adjacency matrix of, at least over F2, namely the loopy graph you get by replacing each black vertex with, well, an uncolored vertex that has a loop there. So just the coloring is just going to be loops or non-loops. So you can think of all of this. If you don't like the coloring, you can always think of it in terms of loopy graphs. So now something to note, that took us embarrassingly long to notice, that pressing a vertex is actually Gaussian elimination over GF2. So here's a picture, right? So here's that graph. Let's say you go to press vertex 1. What happens when you press vertex 1? Well, for example, vertex 1 should get everything zeroed out, right? So it should get 0 in the augmented adjacency matrix that you end up with. And all of its edges should get 0. So it should have 0 on the first row and column of the resulting matrix. And then also, for example, edge 1, 2 here, right? So 1, 2 lives, where is that? That's right here. That needs to get zeroed out, and so does this one. And so we're doing that by adding, if you perform Gaussian elimination, that's exactly what happens. So every vertex that's adjacent to that original vertex that we pressed has the edges to that vertex flipped. And the ones that are not adjacent to it have nothing happen to them because we're not applying Gaussian elimination. Now, it's not all of Gaussian elimination because you're not allowed the pivoting move, right? You're not allowed to actually move to swap rows. But everything else is allowed. So we're going to try to go down the matrix, performing Gaussian elimination row by row. And you're not allowed to skip or swap, right? Which is normally allowed in Gaussian elimination. Also, a small difference with Gaussian elimination, we're adding the row to itself. So you Gaussian eliminate its own row. To use that in a horrible verb way. So the theorem is that, well, given a graph, and now this is more or less immediate from what I just said, the number of vertices in any pressing sequence is the same, no matter what the pressing sequence is. Which is a little bit surprising. A priori, it's not obvious that should be true, that every pressing sequence has the same length. And the reason, the simplest reason to explain this, is that it's just the rank of that matrix over GF2. Furthermore, that means that a bicolored graph has a successful pressing sequence that actually goes through every single vertex, if and only if it has full rank, if and only if the matrix is invertible. So, by reordering the rows and columns of the adjacency matrix, that is, conjugating by some permutation matrix P, you get the following theorem. Given a bicolored graph G on n vertices, the following are equivalent. Pressing 1 through k in that order is a successful pressing sequence. The adjacency matrix can be factorized as a lower triangular times an upper triangular of rank k, because you can use Gaussian elimination to get an LU factorization. They're almost the same thing. And so the existence of this LU factorization is basically just saying that you perform Gaussian elimination. Now this is a little bit surprising and definitely not obvious that this is equivalent. You can actually take L to be U transpose. So it has what, if you're familiar with the complex matrix setting, this is called a Cholesky decomposition, U transpose U. Plays an important role in the theory of semi-definite matrices. The idea, it's actually equivalent to the existence of an LU factorization to have this, but not in general, right? So this is over F2, it's a very special setting. And then also equivalent to it, and this looks just like Sylvester's condition for semi-definiteness, if you're familiar with that. The first leading K principal minors of the adjacency matrix are non-zero, and the rest are 0. So that looks like this, just a little schematic. All the green submatrices, these are the leading principal minors. Those all have determinant 1 actually, because that's the only way you could be invertible over F2, and 0 out in the red area. Right? That's equivalent as well. Also equivalent is that the subgraph of the loopy graph that you get from G, induced on the first J vertices, has an odd number of perfect matchings for 1 up to K, the length of the pressing sequence, and not afterwards. So recall that you have a graph that has a successful pressing sequence of full length, that is length equal, you actually have to press every single vertex at some point, if and only if the matrix, the adjacency matrix, is invertible. So if we assume invertibility, then the previous slide gets a little bit simpler and nicer. The identity permutation as a successful pressing sequence is equivalent to A, having a Cholesky decomposition where U is actually invertible upper triangular. All the leading principal minors are non-zero. And the subgraph of the loopy graph induced on any initial segment of vertices has an odd number of perfect matchings. Those are all equivalent to each other. Now you might have asked, what does he mean perfect matchings when there's loops? All right, so let's use the definition. A matching is a set of non-incident edges, a family of pairwise non-incident edges. And a perfect matching is a matching where each vertex is incident to at least one of the edges of the matching set. If you use that definition, then this, for example, is a perfect matching in the graph that I keep coming back to, right? So we use the loop at 1, use the loop at 3, etc. And just to show you that induced subgraph on an initial segment of vertices, there's the whole graph. If you look at just vertex 1 there highlighted in red, it's only got 1 perfect matching because you have to use the loop. If you use 1 and 2, it's only got 1 perfect matching because you got to use 1, 2. Actually, 1, 2, and 3 also there's only 1 because you got to use 1, 2, and 3, the loop at 3. Still there's only 1 because now you have to use 2, 4, the loop at 1 and the loop at 3. Still there's only 1 when you added 5 because now you have to use 1, 5, 2, 4 in the loop at 3. Still there's only 1 because, well, it's harder to see now. I guess you got to use 1, 5, and 2, 4 in the loop at 6 and the loop at 3. And now, okay, finally there's more than 1, but it's an odd number, right? And then there's an odd number also in the whole graph. There's 11 of them. Not so obvious by inspection. You might ask, why is this, what does this have to do with all this invertibility and the fact that those principal minors are non-zero? Well, the idea is that a loopy graph has an odd number of perfect matchings if and only if its adjacency matrix is invertible. And the reason, this is actually something we stumbled on, it was basically simultaneous, some other work that had been done. It's essentially the same result, but without the loopy part. It's still true even if you allow loopiness. So the proof of this is just the fact that the determinant equals the permanent over F2. Really handy fact, right? So the thing is that you can write the permanent, which counts the number of perfect matchings still even for loopy graphs, equals the determinant, equals, okay, you get the cycle decomposition, you get permutations, and then you break up into cycles. For permutations, the permutation expansion of determinant. And how many terms does each cycle, each disjoint union of cycles contribute? Well, you get 2 to the number of ways of orienting the cycles, except cycles of length 1 and 2 don't have 2 orientations, they only have 1. Anything bigger than that, things that are actually a cycle, that are not, you know, a loop or a dimer, yeah, sure, a digon. It's 2 to the, so Z of C is the number of cycles, or number of circuits of length greater than 2. And C, this is ranging over all the vertex circuit covers. So this is a family of closed walks that visits each vertex exactly once. Well, you can see that these terms are all 0 over F2, you know, unless your vertex circuit cover is made out of only digons and loops. Those are perfect matchings. And so this just counts the number of perfect matchings. Of course, it's over F2, so you only get the parity. But it's the parity of the number of perfect matchings. So if there's an odd number of perfect matchings, the determinant, and therefore the permanent, is, I should say it the other way around, is 1. and otherwise 0, and so it detects the invertibility of the adjacency matrix. Now, another theorem, we go to
300.
3. So another theorem that it turns out is it's a little bit hard to read, but is really handy. Relates, you might ask, what's the relationship between two pressing sequences? If I have one pressing sequence, can I get the rest of them? So here's the thing, these people are studying this stuff for the purpose of doing genomics. Want to be able to study the statistical properties of the space of all evolutionary histories. They want to know, like how often, or what's the likelihood that gene X was next to gene Y at some point during evolutionary history? That's a reasonable question to ask. And for various reasons, may be important to a biologist. So you'd like to be able to enumerate them all. And so there's this question like, okay, can you get all of them? Can you even say how to get from one to another? What does the space of all the pressing sequences look like? So here's the equation that relates them. If you have an ordered, simple pseudograph, so this is a loopy graph that's got an ordering on the vertices. So pseudograph is another word for a loopy graph. But you allow multiple edges usually in pseudographs, so I have to say simple. OSP, ordered simple pseudograph, G, on n vertices. It has, suppose it has the identity permutation as a pressing sequence. So as you say, it's been pressing ordered. It's ordered in a pressing order. And let U be this Cholesky root. It's a kind of like a square root, but not quite. Let that be the Cholesky root that's guaranteed by the previous theorems of the adjacency matrix. That if you have another permutation, which is given by the permutation matrix P, that's also a pressing sequence. If and only if there's an orthogonal matrix Q. Now this is over F2, remember. There's an orthogonal matrix Q and another upper triangular matrix V, so that if you right multiply U, the Cholesky root, by P, then you get the orthogonal matrix left multiplied by the new upper triangular matrix V. The idea is that U and V are going to be your two different Cholesky roots corresponding to two different pressing sequences, and P is going to be the thing that transforms one pressing sequence into the other. Because we've assumed the identity permutation is one of them, P is the pressing sequence. That is what happens when you apply P to the identity. And furthermore, U and P actually determine Q and V, because you can always take a QR factorization of this, and it gives you Q and V. So, in fact, you could sort of pick any two of these things and it determines the rest, more or less. With some exceptions I'll come back to in a moment. So this is what I'll refer to as the key equation, UP equals QV. Upper triangular times our new permutation, there has to be some orthogonal matrix so that Q times some upper triangular matrix V gives you that same UP. All right, notice if you right multiply a matrix U, an upper triangular matrix U by a permutation P, in general it's not going to be upper triangular anymore. So think of Q as correcting that. You're fixing it, you're turning it back into an upper triangular matrix by left multiplication. So you can use some of this theory to get some fun results like this one. The average number of pressing sequences in a random bicolored graph on n vertices, it turns out, is exactly n factorial over 2 to the n. Notice n factorial is the biggest it could be. If you have an empty graph that has no edges, all black vertices, then it's got n factorial pressing sequences. Any order, you can press the vertices in any order you like, and there's no edges to worry about. You just eliminate the vertices one at a time, and eventually you end up with the all white, no edge vertex, no white vertex graph. So this is the average number, so it's a 2 to the n factor smaller than the max. We don't know how tightly concentrated it is around that. Some questions about that. There's something that came up as we were looking at the set of all, at this point we're starting to look at, okay, how can we list all of the pressing sequences of a graph? We'd like to understand it. We started discovering graphs that only had one pressing sequence. And, at first, I mean, we knew of one right away. This path that's only got one black vertex. You have to press that black vertex, and then press the only black vertex you've created, and then press the only black vertex you, etc., right? So there's only one pressing sequence. If it's a path, it's only got one black vertex at the end. But these other ones, where are they coming from? Right? Like, we had no idea where these other ones were coming from or how to even construct them. But when we started enumerating them, it turns out, so I think I wrote something in Sage to just count how many of these there were. And typed in the sequence that we got to, however far we got out to, into the OEIS. And it came up with something. In fact, something really simple, namely this thing. So ignore this formula for a second. What's happening here is you're multiplying by 2, multiplying by 3, multiplying by 2, multiplying by 3, multiplying by 2, multiplying by, that's all. Right, so the sequence is basically root 3 to the n, but then there's this funny business with it getting multiplied by 2 and then 3 halves, 2 and then 3 halves, etc. So theorem with Hayes that the number of uniquely pressable graphs on at least 2 non-isolated vertices, because there's a little bit of a hiccup. There's a similar formula, but it's not as nice if you allow isolated vertices, is this sequence. And you might think something that has that simple a description would be straightforward to prove. It took quite a bit of work. It's like a 20-page argument. So, by the way, I didn't say up to isomorphism or not here, right? And you might have been wondering, is he talking about graphs that have been labeled or not? And it doesn't matter, because if it has a unique pressing sequence, that's your labeling. It has a canonical labeling. So actually, it's up to isomorphism or not, either way. We're counting the same thing. So the proof, as it turns out, is more or less a quick consequence of the following result. Is a characterization of the uniquely pressable graphs. So a uniquely pressable graph G, so we have an ordered simple pseudograph G, and it's got no isolated vertices. It's uniquely pressable if and only if some Cholesky root U of the adjacency matrix has some 4 properties, and I'll tell you what they are in a minute, 1, 2, 3, and 4. It has some 4 properties. And just to point something out, I've excluded, I've said no isolated vertices. I could have just said connected. That's equivalent under the rest of the hypotheses here. Also equivalent that it has, the adjacency matrix has full rank. So there's a few different ways of stating this. I just chose the no isolated vertices version. Here are the 4 properties. They're a little strange, so I've drawn a picture. So here's our Cholesky root. So remember, the Cholesky root is a matrix over F2, so it's only got 0s and 1s. So this is a picture of where the 1s are, right? So I've grayed out any location where there's a 1 sitting there. And then, of course, I drew a red line on the diagonal of the matrix so that you can compare the heights of the columns. So the first property is that the 1s are consecutive upward from the diagonal. That is, there's 1s on the diagonal, which you're certainly going to need if it's going to be invertible. And then there's 1s above it and above it and above it, and then the 1s stop somewhere and they never restart. Right? So there's a stack of 1s starting at the diagonal, and then nothing above it. All 0s above it. Second property is that the column weights, which is the number of 1s in each column, the column weights are non-decreasing. So notice the column weights are 1, 2, 2, 2, 2, 4, 4, 6, 8, 9, 10, it looks like. That's non-decreasing. Also, something a little bit stronger than this non-decreasing property, but doesn't imply it. So I guess not actually stronger. If the weight goes above 2, so the first time the weight goes above 2, then it starts being actually increasing, not just non-decreasing, but in steps of 2. So if you look at this, the first time it goes above 2, leading from left to right, is this column is weight 4, right? That column of weight 4, 2 steps later, this column is strictly bigger, a strictly larger weight. And then that keeps happening. So the weights have to go up 2 columns later, once it goes above weight 2. By the way, if all the weights are 2 except for that first one, which is 1, then that is that path that's got the 1 black vertex over 1. That's the Cholesky root of the associated adjacency matrix. Also, a slightly funny condition, if any of the weights become odd, then all of the weights after that are the entire column. So the stack of ones, once you get an odd number of ones in one of these columns, the stack has to go all the way to the top of the matrix and stay there for the rest of the matrix, reading left to right. So if you notice, the first time it became odd, which is here, it's 9. Well, the next one's 10. You could have, following the 1, 2, and 3, these rules, it could have been 9 in the next column, but this last one prohibits it. So once it becomes odd, you get these full weight columns after that. It turns out these 4 properties are equivalent, not obviously, to it being, the original graph being Cholesky Pressable. And also, by the way, this gives you a quick algorithm for detecting whether a given graph is uniquely pressable. You just find a Cholesky root and make sure that it has these properties. Which is, it's very fast, actually. The finding the Cholesky root part is actually the slowest part.
It says if and only if some Cholesky root?
Yeah, so if some, then all, because there's only one. Okay. So, let me talk a little bit more about this, this key equation. The key equation we'll call UP equals QB. U upper triangular, V upper triangular, P a permutation matrix, and Q orthogonal, and everything over F2. So suppose this were satisfied by Q being P. Notice permutation matrices are orthogonal, right? Their transposes are their inverses, so that's handy. So it's possible that Q could be P, and then B could be U, because that's, of course, also upper triangular. If that happens, I claim that P is actually an automorphism of the graph. Why? Well, here's the equation you get, right? Well, multiply both sides by their own transpose. We've gotten in the habit of calling this Cholesky squaring. Not quite squaring, right? So you expand it out, and then, well, on the right, that is the adjacency matrix because P transpose P is the identity, and U transpose U is the adjacency matrix, because that was the Cholesky factorization. On that side, you're getting P transpose times the adjacency matrix times P, as you're conjugating by the permutation matrix. So you just relabeled the vertices of the graph in such a way that it preserves the adjacency matrix. That means it's an automorphism. Right, so the idea is like relabeling, what this sequence of equality says is that relabeling the vertices by P does nothing. So if this holds, then P was actually an automorphism of the graph. Now, actually, I can say more than that. Suppose that UP equals PU. Well, then, of course, P transpose UP equals U. Everything's invertible, right? Because this is all in the invertible case. So if, notice this actually says something more than that it's just an automorphism of G. It says that P is an automorphism of the directed acyclic graph, whose adjacency matrix is the upper triangular matrix U. If you have an upper triangular matrix U, you can think of it as a directed acyclic graph. So this equation says that permuting the row and column labels, you have to permute the row and column labels using the same permutation. Permuting the row and column labels of U preserves U. In other words, it's a relabeling of that diagram that just gives you back the same diagram. So it's actually more than it just being an automorphism of the graph. It's an automorphism of this digraph, which I'm going to start referring to as the Cholesky dag of G. Right, now remember, G has an ordering assigned to it. So U comes from that ordering. And so there are maybe multiple Cholesky dags for a graph. In fact, usually there are. And something also to note, there's a group of automorphisms, of course, of the dag. Well, it's a subgroup by the calculations you just saw. I mean, you might have to check it, but a very quick calculation. It's just a subgroup of the automorphisms of the graph. And it actually can be a strict subgroup. So there may be fewer automorphisms of the dag than of the graph. And then something else to note, and this isn't maybe as obvious from what I've said so far. The Cholesky dag of G is what we call instructional. It's got the instructions for how to press. So it says that, basically, it says that V has an edge going to W in that dag. That happens precisely when at some point during the pressing sequence, you hit V, you go to press V, and it flips the state of W. So it's the instructions on which vertices affect other vertices. The DAG actually encodes the entire process of pressing, not just the original pressing sequence, but the process itself, right? So it's sort of the instructions for performing the Gaussian elimination.
Are the vertices ordered at this point?
Yeah, these are all ordered simple pseudographs. That's right, it's always going to be ordered for us. Now, so there's this relation, which I'll call squiggle. If you think of pressing sequences as being, they're permutations, so we can think of them as permutation matrices. So P squiggles P prime, if P prime can be obtained from P by an automorphism of the DAG. So, there's this, you can basically collect the P's in the piles where the pressing sequences, where they correspond to the same DAG by an automorphism. So, easy to see that it's an equivalence relation, and multiplication by an automorphism of the DAG is what takes one to another. And furthermore, the equivalence classes are entire orbits of the automorphism group of the DAG, which I'm denoting DG. Now, there's an equivalence relation on those equivalence relations. So we have these squiggle equivalence relations, and then there's a equiv equivalence relation, which says that P can be obtained, or P prime can be obtained from P by an automorphism of the group, because remember, it may be bigger, it may have more automorphisms than the underlying DAG. If that happens, well, okay, so this is well defined. It's an equivalence relation. And how do you get from one of these equivalence classes to another? Well, it's multiplication by a left coset of the automorphism group of the DAG in the automorphism group of the graph. And furthermore, everything that you get by multiplying by one of these cosets is actually one of these equivalence classes. So you don't miss out on it. There's another equivalence relation on the squiggles, right? So forget about the equivs for a second. On the squiggle, I guess what is that? Sim? No, that's sim. That's approx. So on the approx equivalence classes, there's a sim relation. There's not enough symbols for equal. Sorry. Which indicates that P prime and P give rise to corresponding Cholesky DAGs, meaning they have the same transitive closure. So now we're going to take these equivalence classes under approx and put them in piles according to whether the corresponding DAG actually has the same transitive closure. Well, of course, two DAGs that have the same transitive closure, you just think of it as corresponding to the same poset. So really, these equivalence classes, which are well defined, and it is an equivalence relation, they're posets. So they're posets that index these piles of pressing sequences. And you'll see some examples in a minute. This is getting like sort of silly with the number of equivalence relations. There's another equivalence relation on these things. I should comment, this is maybe the big like punchline of all of this slide and the previous one. The original pressing sequences in these sim classes, because these are actually equivalence classes of equivalence classes, but if you dig down into the bottom equivalence classes, they're piles of pressing sequences. Those pressing sequences are exactly the list of all linear extensions of the corresponding posets. They're the complete list of linear extensions for those posets. You'll see an example in a minute. So furthermore, maps between the posets inherited from the maps on these equivalence relations come from the left cosets of the symmetric, so I mean just the permutation matrices here, in the orthogonal group. That comes from that key equation. And then there's another equivalence relation, delta, triangle, which indicates that P prime and P come from the same graph automorphism, and it's well defined, and you get everything that you can get by multiplying by an element of the appropriate quotient group actually gives you something that is one of these equivalence classes. All right, so just a picture. There's these DAG automorphism equivalence classes, which are coarsened by the graph automorphism equivalence classes, also simultaneously coarsened by having corresponding to DAGs with the same transitive closure. And then there's a common coarsening of those two, which is these deltas, which are correspond to isomorphic posets. So refinement is going from bottom to top, or coarsening top down. So here's a picture. This is our graph G. There is its augmented adjacency matrix. There is its Cholesky factor. So if you take that transpose itself, you get this A. That's actually the DAG. Now, don't be misled into thinking you can always just take the upper triangular part of this thing. It doesn't usually work. It just happens that this is a small matrix. I'll give you another example in a minute where it doesn't work. This is the DAG for it. Because it is just chopping this into its upper triangular part, it's just an orientation of this graph, the DAG that you end up with, but only in a special case. And so you get this DAG, and its transitive closure is this poset. So the yellow blobs, this yellow blob is actually the identity permutation and also all of the automorphisms of this original DAG. The green blobs are all of the automorphisms of this, of which there are 8, right, because it's a D4. There's 8 automorphisms here. If you apply them to the identity permutation, you get all of these 8 in the green blob. And that happens in each one of these piles. And then cutting across the piles, cutting across the green piles, are these pink piles that correspond to 2 different posets. Notice these are, although isomorphic, they're not isomorphic with the labeling. So you really do have to switch the 2 and the 4 and 3 and 5 to get this. So this first poset corresponds to the top pink blob and these 5 yellow blobs, and the bottom pink blob corresponds to the second poset. You can see the partitioning of the Presing sequences here. And all of the linear extensions of this poset are written here. These 20 sequences are the linear extensions of this poset. And these 20 are the linear extensions of this poset. They're the complete list of them. Here's another slightly more complicated, but maybe more illustrative example. If here's your graph, here's a DAG for it. Here's how the piles look in this case. So there's, I don't know, how many Presing sequences do we have? 60? No, 48 Presing sequences. And that's, I think I multiplied correctly. There's 48 of them. These yellow piles, again, correspond to an individual Cholesky DAG. The yellow blobs, or the green blobs, from applying all the automorphisms of this thing, of this graph. And then the pink blobs come from the automorphisms of the corresponding posets that I've drawn here with them. And then the blue blobs come from the big coarsening, where you're going to get isomorphic posets inside. So notice, right, all 4 of these are isomorphic without the labelings. And these 2 are isomorphic to each other. But these are definitely non-isomorphic across, right? So even without the labelings. So just, for example, these Presing sequences, this poset, come from this DAG. That's actually, I think it's this one. And you can see, it's not actually, this DAG is not actually its own transitive closure. So it's not the full poset. You have to take the transitive closure. For example, 1 doesn't have an edge going to 2, but there is a 1 to 5 to 2 path. So it's not actually transitively closed. All right, so some questions about this. We have a lot of unanswered questions. There's a little bit of evidence that counting the number of Presing sequences is GI complete. That is, it's the same hardness as graph isomorphism, which surprisingly is the same hardness as just checking. So checking whether 2 graphs are isomorphic and counting how many isomorphisms or automorphisms there are of a graph, or isomorphisms between 2 given graphs, are all equivalent problems. They're GI complete. But because some of the, obviously, like there's some automorphisms involved there, so we thought for a while maybe this problem is GI complete. Now I'm fairly convinced that it's Charpy hard. If you're not familiar with Charpy, these are the problems that count the number of successful paths in a p-time machine. Right? So it's the number of two-set solutions, or the number of three-set solutions. There are some surprising examples of Charpy hard problems, like counting the number of matchings. It's polynomial time to tell if there's a perfect matching in a graph, but surprisingly it's really hard to tell if there are, how many there are. It's actually easy to approximate, but it's hard to tell how many there are exactly. It's Charpy hard to tell how many there are exactly. It's as hard as computing the permanent. That's the, if you like to think, like have a paradigmatic problem in the back of your mind for what Charpy hardness is, it's computing the permanent is Charpy hard, as Valiant showed in 78 or something. So we think it's Charpy hard. Of course, Brightwell and Winkler showed that counting the number of linear extensions of a poset is Charpy hard. But we've got multiple posets for each graph. The number of pressing sequences of each graph is the sum of the number of linear extensions of all of its Cholesky posets. But going the other way is how you would have to show Charpy hardness directly from Brightwell-Winkler. So we're not there yet. But no, strong reason to think that it is Charpy hard. Which would be nice that another sort of fairly natural Charpy hard problem. How about, we actually don't know how to sample asymptotically uniformly from the pressing sequences of a graph. So it turns out actually all of this stuff came from that problem. Because, you know, the biologists looked at this and were like, we have no idea what all the pressing sequences look like, but maybe we could just do a random walk in the space of pressing sequences, and we'll have an MCMC algorithm that gives us a asymptotically uniform distribution over the pressing sequences. And then we get answers to statistical questions about that space, like how often is it the case that gene X was next to gene Y during the evolutionary history of the organism? Things like that, right? Well, we actually don't know of a reasonable, I should say, MCMC for the pressing sequences. But there's a proposal out there by Istvan Miklos and others that they call the pressing game conjecture. So basically the question is, does the following MCMC work? We're going to take a pressing sequence and change it to another by at most 4 edits, by a 4-point edit. I am almost certain, and I've argued at length with him about this, Miklos about this, that this is not even connected. That this, you can't, there's going to be components in the graph that you're walking around on here. But let alone showing that it rapidly converges, that it's rapidly mixing. But we're not there yet. That's actually, Hayes is working on that now. But just to show you that it's tight, if it is true, here's a graph where the edit distance between its pressing sequences, actually you do need 4. You need to be able to make 4-point edits. It actually only has 2 pressing sequences. Another fun question, so we know the graphs that have exactly 1 pressing sequence now. What about the ones that have 2? We don't know, we have no idea. So here's one that has exactly 2 pressing sequences. Here's one of them, here's the other one. If I turn them sideways so you can actually see them, 1, 5, 4, 6, 2, 3 with this labeling, here's another 2, 3, 4, 6, 5, 1, 5. You have to, if you're gonna turn one of these into the other, you have to edit 4 different locations in the permutation. There's no way to get from there to there without editing at least 4 points. So that's got a graph that if you only allow edit distances of less than 4, it's going to be disconnected. So you definitely need 4. But surely 4 is not the truth. We have lots of reasons to think it's not the truth, but egg on my face if it is. But thank you.
Questions? If 4 is supposed to 5? No, it's some function of the length, right? So a function of the size of the graph, I assume.
It's.
So what do you assume it is? Is it some function of the number of vertices?
Yeah. So definitely I mean, very strong sense that it goes to infinity. There's a kind of heuristic argument that it's maybe even as big as n over log n. Yeah, this is sort of very, a very strong sense, but no proof that the mid-edit distance is going to infinity.
Several, but I'll ask one. Since you're talking about linear extensions in a poset, does the dimension have any meaning?
Not something I've considered. I don't know, that's something to look at, because we've been trying to study, basically, so for each graph, you get some pilot posets. And the question is, you know, when can a poset occur just by itself? Because if every poset can occur just by itself, then you've reduced it to bright well Winkler and shown that the problem is Charpy hard. Well, not every poset can occur by itself. But maybe they only occur with only one other poset or something like that. So if you understood which posets could co-occur as these Cholesky posets of a graph, then you might be able to get closer to showing Charpy hardness by solving for the number of linear extensions of a given poset. And I wonder if it might be the case that the dimension of one of the posets says something about the dimension of the other ones that can co-occur.
Yeah, because if it's unique, then the dimension is 1, right, for every poset. If it's one of these unique pressing sequences,
Yeah.
the dimension has to be 1. Or am I misinterpreting?
Yeah, it's just, you just get a chain because it's only got one linear extension. Yeah, certainly, like, it's natural to ask, like, if dimension's playing a role there. Interesting.
No more questions. Let's say you try again.